X. Hi everyone, welcome to our series of engineering analysis with SolidWorks simulation. Our first study is quite basic. It's related to static analysis of a simple plate. It's actually a steel plate that is supported and loaded. As you can see here on this face, we would apply a force of 100,000 newtons tensile load, and the opposite side we'll apply our fixed constraint. We'll learn quite a bit about SolidWorks simulation in this tutorial. Let's jump over to SolidWorks and get this done. Let's begin by navigating to our file, so we can open it from here or here. Let's click on hollow plate, open that. Now that is open, what we can do is navigate to our gear icon where we have add-ins, active add-ins, SolidWorks simulation, startup. Those two check boxes, make sure they are selected and click OK. You can access the simulation from here. These will be grayed out because we haven't set up our study. So if you actually right click, tabs, and you come here, your simulation, if I tick that, it's no longer here. So tabs, and then you check simulation, then you have the option from here. Also, sometimes this is unpinned. So if I click outside here, it's no longer there. You come to your SolidWorks icon, you come over to simulation, and let's click on options. Let's go to our default options. For the unit system, we're going to use SI, the length, meters, temperature, Kelvin, the angular velocity, radians per second, pressure stress, make sure that's set to MPa, and then you can come down to mesh, make sure the mesh quality is set to high, the mesh parameters under measure type, standard, everything else is as default. Also, you can make sure that the hide excluded bodies and show study material appearance. Make sure this checkbox is unselected, and let's click OK. Now we need to create our study. Okay, now let's click New Study. Let's expand this box a little bit. With static selected, we're going to change the name. The name of that would be tensile load. Once you created your study, you will have your study simulation window. So under tensile load, let's right click on hollow plate, and we're going to add our material. So click here, apply, edit material, and make sure you add alloy steel. So sometimes it's here, you can search for it here. You can scroll down and you click alloy steel, make sure the units are set to MPa, and then you click apply. After you finish clicking apply, you click close. Okay, and you will see here alloy steel next to the name of our part file. Now let's right click on fixtures, and we're going to add a fixed geometry. Let's use the middle mouse button, scroll around, and we're going to select this face. and we're going to click OK. Now let's add our load. So right click here and we're going to add a force, and we're going to click this face. We're going to use the reverse direction, and that will be 100,000 newtons, and click OK. You can come here and go back to trimetric. Now let's add our mesh. So right click on mesh, let's create mesh. It's currently set as default, so if we go to mesh parameters, you can see the standard mesh is selected, and here are the actual values. And then let's use a coarse mesh. With that, it's easier to conduct our simulation. However, finer or smaller meshes give us more accurate results. But for now, let's use coarse mesh and click OK. With that done, we can run our simulation from here, or we can simply right click on the name of our study here and hit run. Now let's right click on results option, define edit, click on that, make sure the quantities to save into file, make sure this checkbox is selected, and then click OK. Now on the results, if you right click on stress 1 von Mises and you go to edit definition, you can see that we have other options of displaying our results. So we have chart options, so you can see show different displays. You can also decide how you want to show your maximum and minimum values, as well your results. Let's use floating with 3 decimal places, and we can use this separator for now. If we go down to the color options, you can also change the color. Let's click OK here, and you can actually use your left mouse button, grip that, and move it a little bit more to the right hand side, and then pan this back out as well. Also, if you don't want to see these arrows, so for the external loads, maybe you can right click here and hide, so you no longer see them here. And if you don't want to see these, you can actually right click on fixtures and hide all as well. Now if we right click on this color bar right here, we go to fringe options, you can change this from continuous to discrete. This gives us a more defined analysis. And if we come back here and go back to edit definitions and go back to chart options, we can change the decimal places as mentioned previously, and let's uncheck use the 1000 separator, click OK. You can also animate, you can speed it up, slow it down, and if you explore this, there are so many different things that you can do. Alright, now let's click on displacement, and you can right click on that, edit definition. Let's change the units to millimeters, make sure that show colors is selected. Okay, that looks okay. For the definition, let's go over to chart options, and we have show plot detail, show legend, leave all these ticked, and for the decimals, let's leave those as 2 decimal places, and let's go over to the settings, and leave as is. If we click OK, and let's go back to displacement again, edit selection. Let's drop down advanced, graphic chart, showing it from scientific to floating. And let's say okay. We come here, we go fringe option, we change it to discrete. Let's change it back so we can also do it from here. Edit definitions and chart options. And let's just change the decimal to 3 decimal places. Click OK. Now let's go down to strain. We can right click on it and show, or we can just double click. And the process is similar. We can either right click, edit definitions, or come to the base with the fringe option, discrete, come here, edit definitions, go over to chart options. You can change from scientific, you can change the decimal places as mentioned before, and also other things. We'll leave that as is. If you want to show the mesh, you can actually right click here, and there should be an option to show mesh. You can see a mesh there as well. Now let's create a factor of safety. So let's right click on results, and let's define factor of safety plot. So let's select that, and for step 1 we leave it as all. For the criterion, let's select max von Mises stress. Okay, and let's set the upper limit, and we're going to leave that as 3, and let's use the arrow to go to the next step. For the units, we're going to leave it as ampere. The yield strength, leave as is. Let's go down to our material, that's our alloy. Everything looks okay there. Let's go over to step 3, and let's select errors below factor of safety. Let's use 3, and that looks good. Let's click OK. So where we have the red color, that's actually the areas where the factor of safety falls below 3. The irregular shape of these areas is caused by the coarse mesh used in this particular study. If we go back up to stress, this is actually the stress plot, and here we can see the yield strength, which is 620 megapascals. That's the material yield strength. And as you can see, the highest stress point is actually, let's round off that to 340 megapascals, which falls below the actual yield strength. If we go down to displacement, I double click on that, it shows our displacement. If we right click here and we go to edit definitions and we show colors, we uncheck that and click this check mark, This is just showing you the deformed shape of the object. Okay, let's right back. Let's go right back to here. Edit definitions, and let's show colors. And let's go back to our strain, and you can see our strain plot and results here. And we have covered the factor of safety previously. We have completed the analysis with the coarse mesh, and now we like to change the mesh density to fine and medium also, and compare such with our first simulation where we use the coarse mesh. Now let's copy our study. So where we have tensile load 1, let's right click on that and let's select copy study, and let's give it a name. So we'll call this one tensile load 2, and click OK. And we'll repeat this process. Copy this one, and we'll call this tensile load 3. So 1 would be our coarse, 2 would be our medium, and 3 would be our fine. That's in relation to our mesh. So let's go back here, tensile load 2, as we'll work on this one first. The only thing that we have to do from here is actually create our mesh and run our study. If you come to fix, remember we took it off. So if we show, we remember that we took that off in our tensile load 1, and you see it for the loads. We click on that and click show, you'll see them. So they're actually there. So let's hide them again. And what you want to do is right click on mesh, and you're going to create a new mesh, and this time let's reset. So when we reset, it goes back to the medium mesh size, and mesh parameters, these are medium, and let's click OK. So this is our mesh, and what we want to do is right click on tensile load 2 and run. With that done, we can repeat the steps that we've done previously. We can right click here, we can come down to fringe options, change that to discrete, right click here again, go to chart options, and leave everything as is, as we have done previously. Change that to floating and change the decimal places to 2. If you want, you can uncheck this box and click OK. So if we go back to tensile load 1, we click on stress. As you can see here, our highest stress point was 340 megapascals. If we go to load 2, double click on stress, you can see that has increased to 370 megapascals. Now let's repeat the steps for tensile load 3, and we're going to do this one for a fine mesh. So let's go all the way over to fine mesh properties. You can see the values are much smaller than previously. Click OK. Now if we right click on tensile load and run, as you can see, it's already taken a little bit longer than previously. just a couple seconds longer than the previous runs. And if we right click on stress and we go to edit definitions, we go over to chart options, we come down, we change that to floating, you can uncheck that, 2 decimal places, okay, can right click here, we can go to fringe option, change that to discrete, and let's compare all three now. So look at the highest point here, that's approximately 377. We go to the medium, the 370, and we go to the coarse, that's 340. So we can clearly see that the mesh size is pretty much important in terms of how accurate we want our results to be. Now we are back at our first study. So if we right click on mesh right here and we select details, it will give you some information regarding the mesh, okay, in terms of total nodes, the mesh quality, element size, and you can do that for all three and compare them as well. So if we click here, right click, go to details, see, you can clearly see there's an increase in the element size and nodes as our mesh gets finer. And you can do that for the third one. Right click here, details, okay. Let's go back to tensile load 1. Also, what you can do, if you click on your results here and you go to solve a message, it would also give you the amount of nodes and elements and degrees of freedom, etc. You can save that. If you click save, then you can save it as a Excel file. I've saved it previously, so I'm going to right click here and then I'm going to click open, and I'm going to click open with Excel. Let's see how that looks, and that is now exported. So we have our element size, our degrees of freedom, and the solution time. I don't want to save that at the moment. Cancel that. Click OK. Click back here. Another factor that we can highlight is that if you come to your results and you right click there, you should see compare results. So if we click on that, we can compare 4 different results within one particular study, or we can compare our results for all studies. So you can uncheck the displacement, the strain, safety factor, etc., and just leave stress for each study. So tensile load 1, 2, and 3. Let's just select only stress and you click OK. You can move this outwards. Here once you zoom out in one, and then you can use Control and Pan. Just pan enough, that should be good. You can actually have a visual of all your study on screen, and you can simply come to the legend and compare your results for all of them. So that's another good way, and also you can actually save your file. Okay, let's exit that for now. Now we will repeat our analysis by using a prescribed displacement in the place of a load. Rather than loading it with a 100,000 Newton force that causes a 0.118 millimeter displacement to the load face, we will apply a prescribed displacement of 0.118 millimeters to the face to see what stresses this caused. So if we go back to tensile load 1 and we double click on displacement, this is the highest displacement value, which is 0.118 millimeters, and red, so it's actually on this face. And we'll use the medium mesh for this. So let's go to tensile 2. Let's right click on that. We're going to copy study. Let's name the study prescribed displacement. Okay. We're going to delete the previous applied load. Right click on that. Delete. Yes. Go to fixtures. Right click on that. Advanced fixtures. Let's click on flat faces. I'm going to scroll down. Let's select our face. So go to this face. We're going to change the translations unit to millimeters. We're going to click on normal to face. We're going to scroll down and we're going to give that a unit of 0.118 millimeters. So that would be the unit value. Okay. Go down to symbol settings. We are okay with that. And let's click OK. Now let's create our mesh. Let's select mesh here. Right click on that. Create mesh. If your mesh is anyway here, we need a medium mesh, and that would be in the center of this bar. So you can click reset. We are happy with that. You click OK. And as you can see, this is our medium mesh. Let's run our simulation. Right click on prescribed displacement right here. Run. Let's go to our legend right here. Let's right click on that. We have fringe options. Let's change that from continuous to discrete. Let's right click on this again. Let's go down to chart options. Let's scroll down. We're going to change it from scientific to floating. And let's give it 2 decimal places. You can leave the separator checked or unchecked, it doesn't really matter at this moment. And click OK. Let's now compare our results. So right click on results right here. Compare results. We're going to compare it to tensile load 2. So make sure everything is unselected for tensile load 1 and also tensile load 3, and check stress Van Mises for prescribed displacement. Once those two are selected, click on OK. As we can see, the results produced by applying a force load and by applying a prescribed displacement load are very similar, but they are not identical. The reason for this discrepancy is that in the model loaded by force, the loaded face does not remain flat. Let's now exit our comparison. If you like, you can save the images. So exit. Now let's continue. Let's begin by navigating down to displacement. Now right click on displacement and select list selected. Where we have options, leave it as on selected entities, and here let's select a particular edge. So you can choose any edge, but I'll select this one. Okay, and click update. Scroll down to where you have report options, and let's click on plot. This is actually showing us the displacement along the edge of the force loaded face in study tensile load 2. You can close that. You can accept it if you want. Let's go over to prescribed displacement and click on displacement. We're going to repeat the process. Right click here, list selected, leave selected entities. We're going to select this edge right here. We're going to click on update. We'll scroll down and we're going to select plot. Here is our static displacement plot. We can close that, select OK. Now let's conclude by displaying our resultant force. So let's navigate back to tensile load 2. Right click on results, select list result force, leave options as reaction force. Let's rotate to the side where we have our fixed constraint. Select that, update, and here are the results. If you scroll down here, you have the options to copy such, the option to save. Okay, and then hit OK. And that concludes our simulation. Thank you for watching. Like, subscribe, share. Bye for now.